Hi, I'm Martina Lippi and I'm going to introduce you our work about latent space roadmap for visual action planning. In particular, the problem that we consider is to generate visual action plans for tasks with high-dimensional state spaces, like, for example, the manipulation of deformable objects. So as we see from the picture, we are interested in both getting the visual plan, that's the sequence of images from start to goal, and the action plan, that's the sequence of actions to achieve consecutive transitions. And here, for example, an action is defined as the couple of where to pick and where to release the t-shirt. So the problem is that the traditional planning approaches can be intractable with these kind of high-dimensional state spaces. So we decided to resort to data-driven low-dimensional latent spaces that allow to achieve compact representations. But then the problem becomes how to capture in an efficient manner the global structure of the system in the latent space as well as the dynamics of the system. So to solve this problem, we propose the following approach, where the main component is the visual foresight module that gets the start and goal configurations and produces the visual plan, that is the sequence of images from the start to the goal. And in addition, it also produces a latent plan, that's the sequence of points in the latent space that lead from the start to the goal configurations. And given this latent plan, we have a further module that we call Action Proposal Network that generates the action plan. So by combining visual and action plans, we get the visual action plan. And in this presentation, we will just focus on the visual foresight module that represents our main contribution. So our approach relies on a dataset composed of the following tuples, where the first element of the tuple is the image of the start state, then we have the image of the successor state, and then we have the information of whether there is an action or a no action between these states. So for example, here we have a first example of action pair where there is an action between these two states, and then we have a no action pair where there is no action between these two states. So on the basis of this dataset, we can build our visual foresight module that produces the visual plans. And for this purpose, we first train a variational autoencoder with an augmented loss function that is based on the action-no action pairs. And then we build a graph-based structure in the latent space that we call latent space roadmap. And in particular, the latter allows to capture the global structure and the dynamics of the system. So the basic idea is that each node of this graph is associated with a region of valid states of the system, while each edge is associated with a possible transition between states. So on the basis of this graph, we are able to plan in the latent space from the start to the goal, and then by decoding this latent plan, we can obtain the visual plan. We validated the approach on a real-world experimental setup that's composed of a Baxter robot performing a folding task. So first of all, we define the start and goal configurations. Then we get the visual action plans to achieve the goal configuration, and we select the one to perform. At this point, we can actually execute the first action of the plan. And then we consider that we have a replanning step that takes into account possible uncertainties in executing the action. So now the start state is the current state of the system, and we get again the visual action plans to achieve the goal configuration. We select the one to perform that's now unique, and we execute the respective action. So at this point, we are ready to execute the last replanning step. So we get the last visual action plan, we select the one to execute, and we finally execute the last action that leads to the final configuration. So in conclusion, we proposed a latent space roadmap to perform visual action planning, and we validated the approach on a real-world t-shirt folding task. Thank you for the attention.